Hi everybody, welcome to my talk, which will be about rope simulation in Uncharted 4 and Last of Us 2. My name is Jaroslav Sinecky and I'm a programmer at Naughty Dog. So this talk has three parts. The first is like a general overview of our rope tech, how it came to be, what were the motivations and the features that we needed. And then we'll dive into the technical side of things, and the second part will be about the dynamic rope simulation, and the third part about taut rope simulation, which I'll explain in a little while what that really is. So the rope tech that you can see in Uncharted 4 and Last of Us 2 dates back to 2011. We just shipped Uncharted 3, and at Naughty Dog, after we ship a game, there is usually downtime of several months when people are free to work on their pet projects. And I had this itch to write my own solver. And I look at ropes in our previous Uncharted games, and they had a lot of limitations. And position-based dynamics was already very popular at that time. So I thought a rope PBD solver would be a nice little project for a few weeks to hone my simulation skills. So yeah, after a month or two, I had this rope sim working. It looked better than Uncharted 3 ropes. It had some bending stiffness and was able to interact with some simple collision edges and with animated character collision. So I felt pretty good about it. And just about then, Kurt Margenau, a lead designer at that time, came to my desk and says, "We'll need some better rope for Uncharted 4. So I triumphantly showed him my little rope sim. So that was pretty rare coincidence. That doesn't happen often in game developers' life. But I really had no idea what we were getting into at that time. So Drake was going to have a grapple hook in Uncharted 4, and we wanted to set a new bar for presentation of grapple hook in games. We wanted something more realistic than just a straight line. We wanted to have actual bundle of rope that Drake would have at his belt, and he would reach for it and swing the hook and throw it. We would actually wrap around the branch. We wanted to have slack on different parts of the rope. So we needed a system that would be very flexible. The discretization of the rope had to be completely dynamic, and we needed to change the length of the rope on the fly. And on any frame, we wanted to be able to choose any number of points along the rope and keyframe them. That way we could put the rope into characters' hands and create these rope coils. So here you can see the keyframe nodes on the rope are yellow and the white are dynamic. And in the end, we settled on maximum length for the rope, 14 meters, because I could already see that I was going to have performance issues. I'll talk about it a little bit more in the second part of the presentation. And we created this system where animators could keyframe special values as part of their character animation to tell the game what the character is doing with the rope, like which hand is holding the rope, or if both, then which goes first, how much slack should there be on the rope. But we didn't just aim for high bar in presentation. We wanted to give players also more freedom with the grapple hook. So here you can see you have a rope attach point, and you can drop down on either side of the rock, and the rope will just bend over the edge of the rock, and then you can swing along the wall, and the rope will slide across the rock edges. And I realized my dynamic rope simulation is just an utterly unfit tool for this task. I was already having problems with convergence of the rope solver when the rope was close to taut. And getting it to interact with a collision in a robust way so that we can have gameplay depend on it, that just seemed really hard. So we needed something different, something like this. So here we start with this straight red line that connects the hook and Drake's hand. And then as the hook and Drake move, the line will collide with convex edges and wrap around them and slide along them to maintain the shortest distance between the endpoints of the rope. And this is a completely different thing. So this has nothing to do with the dynamic rope simulation. And I call this taut rope simulation. And the third part of this talk will show a little bit how that works. It didn't seem like a terribly hard problem to me at the beginning, but turned out I was quite wrong about it. So all the grapple hook gameplay in Uncharted 4 depends on this taut rope sim. So even if the rope has some slack, we always maintain this invisible straight line that connects the attach point, the hook, and Drake's hands. And this line has to always stay out of collision, and it tells us how far can Drake go. It also serves as a safe line for the dynamic rope simulation. we have this distance constraint that don't let the dynamic nodes to get too far away from the save line. And as the rope gets closer to taut, then the distance gets shorter. And so for the rest of Uncharted 4 production, all the effort on the rope was focused on getting this taut rope sim working and robust enough so that we could ship the game. The dynamic rope sim was really good as it was, since it was really just a visual icing on the cake.
Got some big plans.
So another idea designers had for Uncharted 4 was to put a winch on our off-road vehicle to create some new gameplay mechanics, and they wanted some pretty long rope for the winch, so they were coming to me from the beginning and asking for a rope that would be longer than 14 meters. I was always saying, no, 14 meters is the maximum. But they really wanted it, so they prototyped with 50-meter long winch rope anyway. Fortunately, the taut rope sim was a great solution to this problem also. The winch rope always has a lot of tension in it, so it was okay to say it will always be completely straight, right? No slack at all. And for the taut rope sim, the length is not really a limitation. There's no regular discretization, so the cost of the simulation really just depends on the amount and complexity of the geometry that it has to interact with. So we shipped Uncharted 4, and then we started pre-production on Last of Us 2. And designers were looking for some new puzzle mechanics. And they were thinking Ellie could carry a bundle of rope on her, and then maybe she could just throw it into the level anywhere and tie one end somewhere and then go around, pick up the other end, and maybe climb up. And it seems like we have this great rope tech, so we should just be able to do it, right? And it was actually difficult to explain why we can't just do it out of the box and why is it hard. The reason is that you lose the safe line, right? Once you throw a bundle of rope into the level, the dynamic rope simulation has to take care of itself. So it has to behave reasonably, always stay out of collision, so that Ellie can go and grab it at any point and use it again. But we decided that it's worth trying, see if we can pull it off. At least we limited ourselves to ropes that are always attached at some predefined points, so you don't just carry a rope that you could throw anywhere in the level. And for Last of Us 2 production, all the effort on the rope was focused on revamping the dynamic rope simulation for a change. So we needed to make it robust so it never clips into collision. The friction needed a lot of work. We tried to make it capable of sliding across collision features, even if you pull on the rope very fast or throw it very fast. And we didn't have any magic when we didn't want to have any magic when bundling the rope, unlike in Uncharted 4 where there is no time for that. So Ellie really meticulously gathers all the 14 meters of the rope into coils. We still use the taut rope sim when we can. It's there whenever Ellie is holding the rope. It tells us how far she can go. It helps guide the throws. And as soon as Ellie picks up the rope, we use the dynamic rope as starting point to quickly find the invisible taut line, which you can see happening in the video now. So it was a lot of work, but the rope puzzles in Last of Us 2 are, it's a very unique mechanic, so you can't really do anything similar in other games. And the rope tech was used for some other elements in both games. The weapon straps are driven by a rope sim. You can see the enemy weapon strap has just like 4 dynamic nodes to make it really cheap. But it's actually enough for quite believable effect. It was used for horse reins. For dog leashes. Or things like this, chained infected. Okay, so all these videos we just saw was to give you some context for the technical part that will come now. So you can understand why we did this and what can be done with this kind of tech. And now let's look at how we actually did it. Before we start, I just want to say all the equations that you will see are here really just for a reference. So you don't have to worry too much about them. You should be able to follow the main ideas anyway. So the second part is going to be about the dynamic rope simulation. And before we get to some more interesting stuff, the next 2 or 3 slides will be like a crash course on basic PBD applied to rope sim. For more details on PBD in general, I'll refer you to this seminal work by Miller and co. But you can find a lot of material around the web on the topic. So let's say we have this piece of rope discretized into a set of connected nodes. The solid black is fixed and the others are dynamic. And in the given moment, we know the position and velocity for each of the nodes. So this is the current state of the rope. Now we want to move forward in time with step delta t. So first we apply some damping, which will reduce our velocities a little bit. Next we apply external forces, which will modify the velocities some more. In this case, we have just gravity, but we could have a wind force, for example. And now we use these velocities to move positions forward in time by step delta t. And this will be the estimate for our new positions. But the new positions do not look right. The rope has stretched. And also, let's assume we have this purple piece of collision geometry here, and the rope is clipping into the collision. So now comes the constraint solving part of the algorithm. So we will need some constraints to prevent rope from stretching and clipping into collision. And since this is a position-based dynamics, the constraints will act on the position of the nodes, and we will directly move the nodes to satisfy these constraints. So first we want a constraint that keep neighboring nodes at the same constant distance, L0, from each other. And this formula looks slightly complicated, but what we're doing here really is very simple and natural. So for the first two nodes, since the first node is fixed, we just move the second node closer to it to fix the distance. And for the second and third node, since they have equal masses, we just move them closer together by the same distance each. And then we do the same for the last two nodes. And here we add the collision constraint, which just means that we will move the node out of the collision. So we will move it along the plane normal until it sits on top of the plane. Now, as you have noticed probably by solving one constraint, we violated the constraints that we already solved previously. So the rope is still stretched a little bit at the beginning and compressed at the end. So we will need to go over these constraints again and again. We'll have to iterate until all the constraints are more or less satisfied. And how do we decide that we are satisfied and we can stop iterating? So usually, either we stop usually when there is some maximum error that's smaller than some threshold epsilon, or when we reach a maximum number of iterations. I can tell you that for PBD, you don't want to use the maximum error criteria, because if you change number of iterations from frame to frame, you're basically changing the stiffness of the solver. So you just want to keep the number of iterations constant. And after we found the final positions that satisfy our constraints, so we need to find the correct velocities. And this is just done by subtracting from the final position from the position on the previous frame and dividing by delta t. And now we have a new rope state for this frame. So that was pretty simple, right? The fact that you manipulate the position of the nodes directly makes it very easy to understand what you're doing. It's also very stable, actually, because, again, as you control the positions, the simulation can't really explode as it easily does when you're solving for some internal forces. So that's why PBD is so popular in games. So if we need for now limit ourselves to, or limit our collision geometry to just a flat ground plane, and the constraint for that can be expressed with this simple one line of code. What I just showed you can be coded in one afternoon, and you can get something like this. So here, the right end of the rope is anchored, and I let it fall. Ellie is just standing there for scale. So that's not bad, right? But there are a few problems you will notice. So one is that there is no friction between the rope and the floor. And when you look closer at the rope on the ground, you can see how it bends at these sharp angles. So real rope has a resistance to bending. So we will want to add some bending stiffness or bending constraints to prevent these sharp angles. So how can we create a bending stiffness constraint? So let's say we have these three neighboring nodes with masses M1, 2, 3, and we want to straighten up this segment of rope by moving them all along the same direction. And for now, let's assume we want to push them all the way into a straight line. And how do we find these unknowns D1, D2, D3? So since the targets are supposed to be on a straight line, that gives us one equation. And then we need to conserve the linear and angular momentum of this little system of three nodes. And that gives us two more equations, and we can find the unknowns D1, 2, 3. So now you might think that I'm taking a lot of liberties here. Why do I move the nodes in this direction, right? I could move them in some different direction. In fact, the most natural here would be probably to pivot M1, M3 around M2 like that to straighten up this segment. So yes, you do have a lot of freedom of how to create your constraints. The bending stiffness could be done in many different ways. I just chose this way because it seemed convenient and because I wanted to avoid using any trigonometric functions to keep the evaluation as cheap as possible. But the conservation of momentum is an important rule that you need to observe. I know you probably heard it many times before, but it's easy to forget. So if you ever get a rope that's twisting on its own like a snake, you probably have a constraint that doesn't conserve momentum and is adding energy into the rope. And now we do the math with the system of equations, and we get this result for the displacements. And each one is a multiplication of the same expression h. And because we don't really want to push the nodes all the way into the straight line on each iteration, it would be way too aggressive. So we introduce this multiplier zeta, and that will be our bending stiffness. So that's the value we can use to tweak how stiff should the rope behave when it comes to bending. And there is one more loose end to tie. So we have coefficient for bending stiffness, but the target for the constraint is still to achieve a straight line. So the constraint will still be trying to move the rope, even just a little by little, until it reaches a completely straight line. But the real rope, up to a certain point, you can bend it without resistance, basically. It has some free bending radius. So we want to do something similar here. So we introduce this alpha f as a free bending angle per 1 meter of rope. And the equations are here really just for reference, but the idea is that simply the bending stiffness will only straighten the rope up to the free bending angle and then stop acting. And now we can look at our rope with this bending stiffness constraint added. And we can see that it does not have those ugly sharp corners anymore. It tends to create these more smooth curves. But we'll need to do something about the friction, right? So friction is problematic with PBD because since you're solving constraints on position level, you don't know what the constraint forces are. So you don't know what's the tension of the rope. You don't know what is the force between the rope and the collision. So that's one drawback of PBD. And because for friction, you need to know the normal force between the rope and the collision, you can't really do that. But one simple thing that you can do is just to remember collision constraint that were used during the solver. So where a node had to be moved out of the collision, and reduce the tangential velocity at that node by some coefficient. And this is done after the solver once you calculated the new velocities for each node. And even though this is a very simple approximation, it might be all you need. I'll show you how it looks when we add it to our little test case. So that looks like a pretty believable rope in this case, and this is all we needed for Uncharted 4, for example, mostly because the rope never had too much slack and was always connected to something on both ends. Unfortunately, it wasn't enough for Last of Us 2. I'm going to show you these two cases where it fails to produce believable results. So in this first case, the velocities are reduced at just a handful of nodes that are in contact with the bar. That's just not enough to keep the rope from sliding back and forth like that. There is a high contact force between the rope and the bar due to the weight of the rope, which means high friction, but we don't know that. And then there is this other case. The rope just keeps sliding and sliding. Yeah, so for our puzzles, it was important that if it looks like the rope should stay up there, that it actually stays up there. So we needed to do something at least a little bit more realistic for the friction. And so one thing we did is this kind of static rope tension analysis. This is done after the solver, and we look at the rope shape and where it touches or wraps around collision and try to approximate what the tension and the resulting contact force and friction of the rope could be. And we use facts like the tension is 0 at the free end of the rope. If the rope bends around the collision edge, we approximate the resulting normal force and friction. If the rope touches collision, we approximate the normal force due to the gravity. If the rope is bending a lot, and it's not because it bends around collision edge, we let the tension fall off to 0. And for a free hanging segment of a rope, we just add tension resulting from gravity. And So this is all very approximate. It's completely wrong when the rope is moving a lot because we don't take velocities into account at all. But that's okay because the friction is not important for us when the rope is moving fast. So this worked fine for us for the rope puzzles. But there was one more thing we had to do. So if you use friction to reduce velocities after the solver step, it is very hard to bring the rope to complete rest. Even if you have high friction and you remove all the velocity from a node, if there is some external force or constraint pulling on the node, even just a little bit, it will move during the next solver step because solver doesn't know anything about the friction. So we introduce the friction constraint into the solver. It's very simple. You just need to remember the original position at the start of the time step. So that's the P line here. And the constraint is pulling the node back towards that position. And we again split the effect into proportional and constant friction. And the constant friction is basically what enables the effect of static friction. So if the node is within the radius SFC from the original position, it will snap back to the original position each time this constraint is processed. And these coefficients, SFP, SFC, are just another empirical coefficients that you'll need to find some values that work for you. But they are informed by the rope tension analysis that I showed you on the previous slide. And here I'll just show you that the friction works much better in these problematic cases. Okay, so one topic that requires some more attention is the convergence, because it's not great. First, if you have a long row with a lot of nodes that goes around collision and you pull on it on one end, it takes a lot of iterations to propagate this impulse to the other end of the rope. Another good example is the rope that's almost taut, like in this little sketch here. So in this case, the distance constraints are pulling the node in direction that's almost perpendicular to the direction in which we want it to move. So they are very inefficient. And from my experience, you basically need a number of iterations that's proportional to the number of nodes in the rope, where one iteration means going over all the constraints in the rope. And that makes the cost of the simulation quadratic in terms of the number of nodes. And it can be very expensive. So what can we do to improve that? One common thing to do is over-relaxation. So basically, when iterating over each distance constraint, we will move the nodes a little bit farther, or in other words, we pretend as if the target distance is a little bit shorter than what it really is. And that helps to reduce the stretch in the rope a little bit faster. And as long as you keep the relaxation factor omega conservative, it should be still stable, at least in my experience. Other common method is multigrid. So you create a series of successively coarser levels of discretization, and you start on solving on the coarsest level, you run few iterations, go to the next level, etc. And this helps enormously with the convergence. Without it, if you have a rope that's almost taut, it basically feels like it would never converge. And one note here is that we had to mark nodes that are at the collision edge, and those had to be part of the coarsest level. Because if you skip them, the multigrid will start pulling the rope into collision and do negative work, basically. And then you will have artifacts in the final results where the rope bends in an unnatural way. So that helped, but the rope simulation was still expensive for the budget we had. Here we have a profile capture on PS4 of some case where the rope was really expensive. And you can see it really sticks out here. So just the solver step is almost 12 milliseconds, and we only have 6 cores on PS4. So if the rope takes over 1 core for like half the frame, that's just not good. So what do you do when you run out of ideas of how to optimize something? Yes, you move it to GPU. And it's not the greatest fit because, as I was saying, the rope solving is inherently very serial process as you're propagating impulses along the rope. We run one wavefront and process 64 nodes at a time, but it's not the same as doing 64 nodes one after each other serially. So in total, you end up doing more work on GPU than you would do on CPU. So this is not the best utilization of your silicon, but we still take it, and this is why. So here you have a GPU profile capture, and it's not much faster. It takes almost 10 milliseconds for the compute shader to finish. But the main difference and why this is much better is that it's just one wavefront running on one compute unit. The PS4 GPU has 18 compute units, and if you make sure your shader resource usage is not too high, several shaders may share the same compute unit, so you're really just taking tiny fracture of the GPU. Okay, I'd like to talk some more about collision. So far I glossed over it, saying you have a collision plane and you need to push the node out. But in real level, you will have to deal with some complex geometry, probably some triangle mesh, or maybe just pile of triangles or some convex shapes. But you still do want to express this geometry in some simple and compact form that can be evaluated quickly, because you're going to iterate many times over many nodes. So what we did is we tried to boil down all the geometry around each node into a set of collision planes. And then we needed to be able to collide with convex edges, so we just marked the pairs of planes that form a convex edge. And each node has maximum of 4 collision planes and 3 convex edges. So this sketch here really represents it's like example of maximum geometry complexity that can be accurately expressed with the collision constraints for one node. And this second sketch shows the edge 1 when we're looking along the edge. And it shows what the collision constraint is doing for the pair of planes N1 and 2. So we have to, since they form convex edge, we have to check where is the center of the node. And if it's in the blue area A3, it collides with the edge. So we have to push it away from the edge. Otherwise, it collides with one of the planes. And this way, the node can slide smoothly across the edge. Here we have a debug draw from the game with the node going through a window corner with some fairly complex geometry. And the way this works is that we first try to estimate how the node might move during the upcoming solver step, based on its current velocity, the direction in which the neighboring nodes might be pulling it, based on how much the closest keyframe nodes have moved. And this gives us ABB around the node. And then we collect all the geometry in that ABB. And then we try to be smart and distill these triangles into our limited collision constraint set. So each triangle gives us a collision plane, and then we see if some of these planes are similar, so we can merge them together. We detect convex edges, and then using current position of the node, try to see which planes are more important than others, or which ones maybe we can ignore completely because they are behind other planes, etc. Here's just a few examples of simple cases where this approach breaks down. So we only have pairs of planes creating a convex edge. We don't have a concept of group of convex planes like this. And it's not trivial to add this kind of concept into the solver. So in this case, if you have a node here, the plane N3 will pull it on the wrong side of a collision, and then N1 and N3 starts to fight over the node. So in this case, the best thing to do is just to discard plane N3. But it's much harder to do this call, to make this call if the node is somewhere here, because if it ends up moving to the left, it will collide with plane N2 like this and create what's called a ghost collision. And here is another simple example. So plane N1 here doesn't have any convex edge, so it works as an infinite plane. And again, it can create a ghost collision like this. So a lot of effort went into these heuristics of compiling complex geometry into a limited set of constraints for each node and trying to make it work as robustly as possible. And it never got totally robust. Sometimes our geometry is very complex and the rope needs to slide across it very fast. So this really here was the crux of the dynamic rope simulation. Fortunately, in Last of Us 2, the area where the rope can be deployed is limited by the fact that one end of the rope is always anchored somewhere. So in the end, we just had to test these areas properly and go and clean up the geo in problematic places. Also, we have a system that allows us to tag collision triangles to either ignore rope or to ignore everything but the rope. So we can create special layer of collision, of clean collision just for the rope if that's needed for some places. Shipping a game where you can do this with the rope anywhere in your level would be much, much harder. And so before we finish the dynamic rope part, I just want to show you a few useful tricks you can do with collision constraints. So before you send them off to the solver, you can look at them and see if there is something suspicious about them that could cause issues. Here we have a node with 2 collision planes. The orange normal indicates the positive side. So the node is basically trapped between the planes. And this would usually happen when some prop or character collision would animate into static collision, most often at least thigh or torso. And it's important for us to never let the rope clip into the static collision. We don't care that much about the character capsules. So let's say the black plane is the important one and the purple less important. So first we'll project the node out of the black collision, and then we just move the purple collision back until it just touches the node. That way it creates space for the node. This pinching prevention is pretty common in cloud simulations, I think. There's another useful trick you can do during constraint preprocessing. I'm going to show you the problem first. It was mostly affecting weapon straps because characters can sometimes animate their hands through collision. And if they're handling a weapon that has strap on it, it can get stuck on a collision and stretch out. It could get pretty severe. I've seen weapon straps from enemy weapons stretched across the whole level a few times. Fortunately, there is a simple trick to prevent that. Here we have a piece of rope with 4 nodes. The yellow node 0 is keyframed, and we know the length of the rope between node 0 and 3. And here we have a collision constraint for the node 3, and we can just measure the distance of this plane from the keyframed node. And if it's bigger than the length of the rope, then we know this plane will stretch out the rope, and we can just ignore this plane. It's very simple but effective. Here's the result. You can see how the constraints are being removed as the strap starts to stretch. Okay, so now we will jump straight into the third part of this talk, which is going to be about the taut rope simulation. And as a reminder, this video shows what we're after. So it's just a line that's able to collide with collision and wrap around it and slide along the edges to maintain the shortest distance between the endpoints. The collision needs to be fully continuous, so no matter how fast the endpoints of the rope are moving or how thin are the collision features, it never clips through the collision. And surprisingly, I didn't find any previous work on something similar, so I'm just going to show you the approach that we took. So we start with this simple case. We have just a straight line segment, AB. The game tells us that on the next frame, the endpoints AB have to move to these new positions. So that's our first movement phase. That's where we want the points to move. And next, we need to check for collisions, and we do that by always moving just one point at a time. So first we move point A and keep the point B fixed. And during that movement, this line segment will sweep this green triangle. So we just need to check for intersection of this triangle with any neighboring convex edges. There's no collision here, so the point A can move. And then we do that for point B, and here the triangle intersects with the blue convex edge. And the intersection point is the point of contact, so we only let the point B move up until the contact point. And we enter a new edge point into the rope, and we can call it a point C. And so, since this collision phase found a contact, we have to terminate the collision phase, and we go back to another movement phase. And the point B still hasn't reached the target point, so that will be the new movement for that point. And I'm going to move the camera so that you can hopefully see better next steps. So from this angle, you can see that the rope is not straightened up, and we will want to let the point C slide down along the collision edge to straighten up the rope. Now, how do we find out how far it should slide? So here we are looking along the edge, and RA, RB are perpendicular distances of the points from the edge. And we can rotate point A into the plane where the edge and the point B are. And here we are looking onto the plane, and we can just draw the straight line between the point B and A line to find the intersection with the edge. And that's where we want the point C to move. And if we go back to the 3D view, so now we know how far we want the slide. We want to let the point C slide along the edge. But this was just a movement phase. So now we know where we want points B and C to go. And we need to go to do another collision phase to check if we actually can get there. And we do it again by moving points one by one. So first we move point C, and we need to check for intersection of edges with these two triangles. It's all good, and then we check this triangle for point B. No collision here, no collision here. And since this collision phase ended with no new contact, we're done, and this is the final position of the rope. So this is the core of the algorithm. We are alternating these movement and collision phases. Movement phase tells us where we want points on the rope to move, and then the collision phase checks for collisions. And if there is a collision, we have to go back to another movement phase to generate new target positions, etc. And if the collision phase reports no new contacts, then we're done. I'm going to show you one more example to explain better the movement phase. So here we have a rope that has 2 edge points already. And now the game tells us that the endpoints have to move to these new positions. And it's not obvious how we should directly calculate how far should the 2 middle points B and C move along their edges to straighten up the rope. So we will only use the first 3 points, A, B, C, to find out where the point B should move to straighten up this segment ABC. Then we do the same for the BCD to move the point C. And then we keep doing that until we find a position where the rope is straightened up, or as straight as it can go given the collision edges. So the movement phase is an iterative process. And this was also just one movement phase. So as long as each point on the rope is moving along the same edge and doesn't change direction, you can keep iterating until we find the target position that straightens up the rope. And now we would have to go back for a collision phase to actually check if we can get there. So there's one problem with this iterative advancement of rope edge points. I'm going to show it on this piece of geometry. So now the upper point has moved to the right, and now we need to slide all these edge points along their edges. But as the edges are getting closer and closer together, the iterative method is getting less and less effective until the points pretty much stop advancing completely. Fortunately, there is a nice way to deal with this problem, since you can basically unroll it all into 2D and solve it in a plane. So as you go along the rope, as long as 2 consecutive edges are lying in a plane, you can keep unrolling onto the same 2D plane. So here we start with edges A and B, and their plane will be our drawing plane on the right. And first we bring the point P0 into this plane by rotating it around edge A. And then since B and C are parallel to each other, we can bring edge E into this plane also by rotating it around edge B. And then we do the same for D and E. And in the end, we also bring point P1 into this plane by rotating it around edge E. And so once we have all this in one plane, we can just draw a straight line between point P0 and P1. And in 2D, it's easy to find these intersections. And then we bring it back into 3D, as we can see on the left side. So the only case when you can't use this trick is when 2 consecutive edges on the rope are skew lines. In this case, you still need to use the iterative method. Okay, so that wasn't that bad. It gets worse when we have to start dealing with intersection of edges. So here we have this rather ugly piece of geometry, but it will serve us as a good showcase to demonstrate how to deal with edge intersections. So our rope has 1 edge point, and as the endpoints are moving, it slides along the edge until our collision phase reports that we hit some collision at this point. And here the important thing here is that our collision detection algorithm has to be able to report all the edges that come together at this intersection point. So we don't want just the first edge, or numerically the first edge, that the rope hits. We want to be able to gather all the edges within some tolerance of the final position. And this kind of numerical robustness is an important part of the whole taut rope simulation. I'll talk about it later a bit more. Okay, so we have this point on the rope that's at intersection of 5 different edges. Now, what should happen next, right? What is the point supposed to do? Should it slide along some of the other edges, or should it stay at the intersection? So to make it easier to reason about it, what we do is that we evaluate all the pairs of 2 edges. So we always only look at 2 edges at a time, and we try to decide what that intersection of 2 edges means, and then we put it together at the end. So before I can explain that better, we need to establish some orientation for the rope. So we choose one end of the rope to be the origin or the beginning, and we establish the orientation that it starts at the origin and points toward the back, toward the end, like that. And we also need an orientation for the edges, so we'll establish the orientation like this, which basically means that if you're standing on the face that's facing the origin of the rope, that's the upper face here, and you're looking along the positive direction of the edge, then the rope has to pass the edge on the right-hand side. Okay. Now, as I was saying, we will be always evaluating one pair of edges. So here we have two edges, A and B, and we found a plane in which these two edges lie, and that will be our drawing plane now. And we orient this plane in a way that the rope is going from our side into the plane. So I can draw the rope crossing the plane like this. And we also have the orientation of these two edges. And according to our rule, the rope has to pass on the right-hand side of each of these edges. So I know that the rope has to be somewhere here, okay? Right, on the right-hand side of A and then right-hand side of B. And I drew the edges as lines that are crossing each other, but in fact, they should either start or end at the intersection. Otherwise, you would have like a T-junction in the collision mesh, and you're not going to worry about that case. So depending on which edge starts or ends at the intersection, we will have different cases. And the first case will be like this. And in 3D, it would usually look something like this. So I call this case inner corner, because it's like a corner where the rope can get caught, basically. And next thing we do is, considering where the previous and next point on the rope are, we evaluate in which direction would the rope slide along each edge if we would only have that edge alone. So we evaluate that first for edge A, and then we do that for edge B. And different combinations of these directions will give us different subcases for the inner corner. So this subcase basically means the rope is trying to move into the corner, and I call it stable inner corner, and that's the case when the rope stays at the intersection. And this one, this subcase means that the rope is abandoning edge B and it's moving or sliding along edge A out of the intersection. So I call it move along A, and this would be move along B. And here we have this other case. And in 3D, it would look usually something like this. So I call it unstable corner. And depending on which way would the rope slide along each edge, we have this subcase, which you can basically choose A or B because the rope is on the vertex basically and can go either way. And then we have a move along A or move along B. And then we have this case where, if you think about it, the rope needs to be on the right side of B, but the edge A will not let it go there. So you can basically disregard the edge B. In 3D, it would often look something like this. So the edge B is basically coming from the side, but the rope can't really interact with it. So I call this case side edge. I had to invent some names for these cases so I can reason about them and write a code for them. And the subcases would be either ignore B or ignore A in this other case. Okay, so we're not done yet, so bear with me for a little longer through this section. The rope can cross the plane of the edges twice. So it comes from the origin, it goes into the plane, and it comes back again. Geometrically, since the rope is at the intersection, it really just touches the plane at the intersection point. But from topological standpoint, it goes into the plane, crosses the two edges, and comes back. And when it comes back, it has to be on the left-hand side of each of the edges for the same reason that it had to be on the right-hand side when going in. And so now let's look at what segments of the edges are we dealing with, because that will give us different cases again. So first, let's consider this case. And maybe this corresponding 3D sketch will make it more obvious what's going on here. So basically, the rope was going over the two edges, and now it's slid onto the corner and is about to slide off. Or maybe not, it depends on the other edges coming into the intersection. But for now, we're only thinking about these two edges. So I call this case outer corner, and the subcases are either the rope goes over A and then B, or first over B and then A. And finally, this last case, or this one, those are the equivalent cases basically. And in 3D, it would be something like this. So the edges would have to be like relatively sharp edges so that the rope can go over them like that. And depending on which way the rope wants to slide along each edge, we have these subcases. which are equivalent to what we already saw before. So we have a stable inner corner, or inner corner move along A, move along B, or we can have also unstable corner. Okay, so now equipped with all this topological categorization, we can look at our test case. Hopefully, working it out on this example will show more clearly how this all works. So we have these 5 intersecting edges here, and we'll call them A, B, C, D, E. And we found out what their orientations are, and then we evaluate the topological case for each pair of the 2 edges, and we'll get this kind of matrix here. And first we look for some side edge cases, and we see that B and E are side edges, so we can ignore these edges. And now we only have A, C, D left, and we see that there is an inner corner, stable inner corner between AC and AD. And if there is any stable inner corner, it means the rope is caught in the corner and stays there. So we just keep the rope point and the intersection. But the endpoints of the rope will keep moving now. So they move just a little bit, but the situation has changed slightly. So we have a new matrix here. The edges E and B switched orientation, but they are still side edges, so we can still ignore them. And there is no more stable inner corner, so the rope should move out now. And instead we have inner corner move along C and inner corner move along D. So we know we will abandon edge A. And then also edges C and D create an outer corner CD. So we will want to split the rope point into 2 points. First will go along edge C and the second will go along edge D. So here it goes. And then we can go back and it will be basically the same thing but in reverse. So at a certain point, the two rope points will get within some tolerance from each other, and we will merge them into 1 point, and then we will reach the intersection, spend a while in the stable inner corner, and then move along A out of the corner. But even just for this case of edge intersection, the situation can change dramatically depending on what the endpoints of the rope are doing. So just for illustration, if the rope ends go like this, then suddenly edges A and B are now forming an outer corner. And then we can do this, which is pretty common, where the rope basically lies within the face of a triangle. And then when it reaches an edge, it's parallel to the edge. So we need to be able to deal with these cases also. So maybe this is a good moment to address this numerical robustness I mentioned before. So when you do any kind of distance tests, like is the rope touching an edge or 2 edges intersecting, you can't just test for some distance being 0, right? You need to use some tolerance. And you want to be consistent with this tolerance. It has to go through the whole algorithm and becomes part of all the collision tests, all the distance or intersection tests. And we use tolerance 0.001 millimeter, which is quite large, unnecessary for just numerical errors, but that way it also covers geometric errors. If you, for example, have 2 boxes and you place them next to each other in your level builder or level editor, it may be that when this geometry comes into the game, the vertices that were aligned are not exactly at the same coordinates, right? And you don't want your rope to slip into the tiny slot between the boxes. And another problem is there are some tests or predicates in this algorithm that are very important, but it can become numerically unstable. Good example is the edge orientation. It's important to get it right, otherwise you basically tell the rope to go on the wrong side of the edge. But sometimes, like in this case we just saw, when the rope is close to parallel to an edge, there is no good way to tell what the orientation should be. So it's just important to tread carefully when writing these predicates and think about what happens in these singular cases and what are the consequences. There's no time to go into the more details, but I just thought I should bring it up because it definitely brings another level of difficulty to the problem. And speaking of difficulties, so the taut rope simulation also never got 100% robust to be able to deal with any geometry that you throw at it. Here are the main reasons why. So it's the numerical robustness that I just mentioned. It's pretty hard to get that to 100% in an algorithm that's fairly complex. The edge intersections prove to be hard too. So the topological classification that I showed you, where we always just look at 1 pair of edges, and we also test in which direction the rope wants to slide by only looking at 1 edge in isolation. So it mostly works, but I did find some obscure cases where there was some more intricate interdependency between the edges at an intersection, at certain angle of the rope going through it. And the algorithm would just make wrong decision. It was pretty rare though, and we didn't have time and real need to dig deeper into all these cases. And one limitation coming just from code design is that we only support maximum of 8 edges per rope point. So if you have a vertex in your collision mesh with a lot of convex edges coming together, and the rope needs to slide over that vertex, we will just randomly drop some of the edges. The result is, in this case, usually not catastrophic, since we have already a lot of edges that will keep the rope more or less on the surface. So I'm going to show you this scene from Uncharted 4. Drake wraps the winch rope around a tree as many times before, and now he's going to drive up the mudslide.
We're all set. Here we go. Easy. No panic! No panic!
So did you notice what the rope was doing as the Jeep slid off? Of course you didn't. It's pretty much impossible to see anything because it happens very fast and there is a lot of particles and the camera is not even looking in that direction. Nevertheless, this was probably the hardest case for the taut rope in the whole game. The reason it was hard is because the rope is sliding very fast across a lot of geometry, and since it's going mostly parallel to the surface, it's colliding with all these edges at very sharp angles and basically hitting all these edge cases and numerically unstable tests. And we could have faked this particular case as literally nobody will be seeing what the rope is doing, but it was kind of nice test case and easy to reproduce. Here is a little more detail and it goes step by step. And so if you pay attention to this place here, yeah, so right now you can see the rope clipped into the collision, but it will recover, it will get pulled out again. And then there is another problematic spot later, I think somewhere here. So this is just to show that not everything was a total success. But it also shows the general tendency in these cases is that even if something goes wrong locally, usually the other edges will hold the rope up and pull it out of collision eventually. So it rarely has catastrophic consequences for the gameplay, fortunately. Okay, so let's wrap it up. So when Last of Us 2 came out, somebody noticed the rope, and there was this long thread on Twitter with also reactions from game developers. And a lot of them saying that seeing this was actually stressing them out and giving them nightmares. Some people expressing their fear that their producers will now ask for the same thing. So this talk, hopefully, if somebody actually tries to implement something similar, will give him some pointers and help avoid some of the pitfalls that we went through. But also I'm hoping this can help make a better judgment of how difficult it is and if it's worth the effort. It can maybe serve as a defense when some game director asks you for a role like Last of Us 2. Because yes, it wasn't easy, over 8 years in development, and even though the rope definitely wasn't the only thing I was doing during those years, it was by far, I would say, the hardest. But your mileage may vary. You might not need everything we did. If you only need some visual elements, hanging ropes or vines or weapon straps, some simple rope PBD solver is actually very easy to put together, as I showed. Now, depends if you need the rope to be long with a lot of nodes, because then maybe you will have to deal with convergence and performance problems. How realistic you need the friction to be, how complex is the geometry, because that's a big one, because that hugely impacts how hard will the problem be. And not surprisingly, if you have gameplay depending on your rope sim, that's when things get hard. So both the taut rope, which drove all the gameplay in Uncharted 4, and the dynamic rope, which we needed for gameplay in Last of Us 2, proved to be hard problems. What I showed you for the taut rope sim may not seem very complicated, but it is a lot of code, a lot of complicated bookkeeping and dealing with edge cases and numerical robustness. So don't underestimate that part, because I sure did. And as I already admitted, even though significant effort went into these systems, we never got them 100% robust to be able to deal with just any geometry. So again, the geometry complexity is the biggest factor here. So if you can limit in any way how complex is the geometry that the rope has to interact with. That's the biggest help you can give to yourself. By limiting the area where the rope can be deployed, or what kind of collision features it needs to interact with. Maybe getting some clean and simple collision authored for these areas, or have some offline pre-processing step to clean it up. So all these things, it's definitely worth looking into. And one last piece of advice. So if you're going to implement something like that, it will not be easy. So it's worth to invest some time into creating some solid debugging tools to make your life easier. One nice thing about a rope simulation like that is that it's a relatively isolatable piece of software. So you can grab a piece of debug memory and use it as a ring buffer and store all your input and state for each frame. And then if something goes wrong, you can pause and step back and look at what failed. You bring up all your diagnostic drawing, and when stepping forward, you can run exactly the same simulation. Our engine is not deterministic, not even close, but the rope simulation is. There is nothing that would be breaking determinism here. So you can find a frame when something went wrong, and then just play that frame over and over and debug it as you want. We even created a rope dump where if somebody, mostly testers, would find something went wrong, they could just dump the ring buffer plus some collision shape data into a file, and then I could load it up on my dev kit and debug it as I wanted. And so this tool was absolutely crucial. We could never ship a game with these rope features without the rope debugger. And that's the end of my talk. So presumably I'm already answering your questions in the chat by now, but you can also contact me at this email if you have more questions or ideas or comments. So thank you for listening.